Here's a sample problem where we try to work through a calculation involving constant acceleration. In this sample problem, we're going to throw a ball straight upwards with an initial speed of 10 meters per second, starting at the ground, and we're going to ask three questions that should be answerable using our two equations. One is, how long will it take before the ball reaches its highest point? We know that the ball is going to go up for some distance, come straight back down again, and hit the ground. At this highest point, how long will it take to get there? Second question is, how high will it go at that point? And the third is, when it finally comes down and hits the ground again, how fast will it be going? So let's take these in order. So we're asking a question about the highest point. Well, at this highest point, we know that the velocity will equal 0. How do we know that? Because up until that highest point, the velocity is positive. The ball is heading upward. Over on this side, though, the velocity is negative. It's heading downward. If it's positive at one moment and it's negative at the other moment, it means it had to go through 0. It was 0 for a short time. So at this particular instant in time, we're going to say that the velocity is 0, and of course velocity is always v0 minus gt. Well, it's v0 plus acceleration times time, but we're setting acceleration as minus g. Because if this coordinate system has y going up, then the acceleration is pointing down. So here's an expression, 0 is v0 minus gt. I can solve for the time. And if I put in what my initial value of v0 was, it was 10 meters per second divided by 9.8 meters per second squared. It says the right units because meters per second will cancel one of these meters per second and leave a second down here in the denominator, which flips up. Approximately, this is 1 second. That's the amount of time necessary to get to the top of the arc. The second part of the question is, how high will it go? Well, we know that y of t equals y0 plus v0 t minus 1/2 t squared. Now, we have to put in some information here. Y at some later time t is what we would like to know. In fact, we'd like to know it at 1 second. But the initial y at time t equals 0, well, we don't know that. Well, actually we do. We are throwing it from here on the ground, so this is roughly 0. And that leaves us with y at that later time is v0 times t minus 1/2 gt squared. And everything here is known. We know what v0 is, we know what the time is, we know what g is, and we know what the time is again. So I'm going to use v0 is 10 meters per second times our approximate value of 1 second minus 1/2. We use g as approximately 10 meters per second squared. We'll put in 1 second squared here for the time t. This is approximately 10 minus 5. And this gives me that y is equal to 5 meters. Notice that the units check. This is meters per second times a second. This is meters per second squared times a second squared. So the ball, if I throw it with 10 meters per second velocity straight up, will go about 5 meters up into the air. The third part of our question was to ask, when is it that the ball hits the ground, and then how fast will it be going at that time? Well, I don't know when it will hit the ground, but we do know that when it hits the ground, that's when y of t equals 0. We can again plug in this is y naught plus v naught t minus 1/2 g t squared, and this term is 0 because it started at the ground. And this is 0 is v naught t. I have 0 equals v naught minus 1/2 gt times t. So either one of two things is true. When a product of two expressions, parenthesis times this other thing, is equal to 0, it either means that the first thing is equal to 0 or the thing inside the parenthesis is equal to 0. So this means either t equals 0 or v naught minus 1/2 gt equals 0. Well, t equals 0 is sort of a trivial case. I mean, both are true. T equals 0 is right when we launch the ball up in the air, so indeed then y of t is 0. That's sort of by construction. That's how we solve the problem. So it's the second one that we're interested in, because that's the case where it strikes the ground again. So I'm going to cross this one out, not because it's not true, but because it's not the one we're interested in when we ask when the ball strikes the ground again. So in this case, the time is 2v naught over g. And if one inserts 2 times 10 meters per second, because that's the v naught we were given, and I use approximate values here of 10 meters per second squared for g, I get that this is about 2 seconds. Notice this is exactly twice the value that it took for the ball to go up to the top of its arc. And that's not surprising. The ball's trajectory is symmetric. It takes a certain amount of time to go up and a certain time to come back down again. And then we want to ask, what was the velocity when it strikes the ground? Well, at that time of 2 seconds, I just again insert into this expression v of t is v naught minus gt. This is 10 meters per second minus 10 meters per second squared times 2 seconds, and one gets minus 10 meters per second. Notice that this is the exact same value or magnitude as we had when we launched the ball. It was launched at 10 meters per second. The only difference is this minus sign that's right here in front. We initially launched the ball with a positive 10 meters per second velocity, and as a result of going up in the air and turning around, it's now got a negative velocity, but it has the same magnitude. That's because we launched it from the same position as when it came back down again, and we'll see soon enough that gravity has a somewhat symmetric behavior here, that it will come back down in much the same way as it went up.